So tonight we're going to be finishing up 5.1. In class we looked at perpendicular and angle bisectors and find out that some kind of special things happen with those. Today we're going to look at those same segments in triangles and see what happens there. Before we do that, we need to define a few words, the first of which is concurrent lines. Concurrent lines are three or more lines that intersect at one point. So it's not uncommon for lines to intersect, but for three of them to intersect in the same place, that's kind of neat. So here, A, B, and C, those lines are concurrent lines. They all intersect at this one point, which is point P. And that point P there, that is called the point of concurrency. So that's the point where concurrent lines meet or intersect. Okay, the point where those concurrent lines intersect. So the first thing we're going to do is look at perpendicular bisectors. So we're going to draw the perpendicular bisectors of this triangle ABC, and we'll find that something kind of neat happens. So here, I'm just going to draw really quickly the perpendicular bisectors of each segment as closely as I can, and I am not perfect at this by any means, but I will get it to the best of my ability. So here are the three perpendicular bisectors of this triangle. So we're going to draw our right angles. We're going to draw our marks, showing that all the sides are being bisected. And we find that when we draw the perpendicular bisectors of a triangle, they all meet at one place. They have a point of concurrency. So we'll call this point P. And for perpendicular bisectors, we call that point of concurrency the circumcenter. Okay, so the circumcenter is the point of concurrency for perpendicular bisectors. So it's the point where all the perpendicular bisectors in that triangle meet, all three. And the kind of neat thing about that circumcenter of that triangle is it actually circumscribes the triangle inside of a circle. That's why it's called circumcenter. And now I am not going to be good at drawing this by any means, but let's pretend that that shape I just drew is a circle, and that it's not some squishy looking oval figure. The center of that circle would be our circumcenter, point P. And so if we were to connect PA, PC, and PB, those would all be radii of that circle. So each one is a radius. Okay, it goes from the center to the circle. So the thing we know about radii in a circle is they're all the same length. The radius of a circle is the same no matter where it is. So here, from the circumcenter to the vertex of each triangle, those segments are going to be congruent, and that is the circumcenter theorem. It just says that segments from the circumcenter to a vertex of the triangle are congruent. So segments that go from the circumcenter to a vertex of the triangle. Remember, vertex just means a point of the triangle. Okay, that would be a vertex there. So A would be a vertex. So segments that go from circumcenter to vertex, those are all going to be congruent. So for instance here, P is the circumcenter of this triangle. From P to B, P to A, and P to C is the same distance, so all of these points are congruent. So where is the circumcenter located? So it's located in different places depending on what kind of triangle you have. If the triangle is acute, meaning all of its angles are acute, the circumcenter of that triangle will be always inside of the triangle. So with an acute triangle, the circumcenter is inside. With an obtuse triangle, meaning it's got an obtuse angle in it, the circumcenter is going to be outside of the triangle. And you can try drawing these. Draw a obtuse triangle on a piece of paper and try drawing the perpendicular bisectors of each side. You'll find that they do meet outside of it. And then with a right triangle, they're actually on the hypotenuse of that triangle. So on one of the sides, specifically the hypotenuse, that side. And so you can see here's P, our point of concurrency. It's on the hypotenuse of this right triangle. We know that that's the hypotenuse because it's opposite the right angle. Not only is it on the hypotenuse, it's actually at the midpoint of the hypotenuse. So it's not only on the hypotenuse, it's at the midpoint of that hypotenuse. So if we wanted given coordinates of a triangle, if it's a right triangle, it's really easy to find that circumcenter. So let's look at an example. I'm going to list all the segments that are congruent to the following. So here, what we need to know is that we've got perpendicular bisectors. So knowing that, I'm going to list all the segments that are congruent to the given one. The first one is BR. So here is BR. It is congruent to RA. Remember that perpendicular bisectors bisect a segment. So BR is congruent to RA. Not RS, RA. So let's look at the next one. The next one we're looking at is BP, this green segment right here. You can see P is the circumcenter of this triangle, B is a vertex. So this green segment is going to be congruent to any other segments that go from the circumcenter to a vertex. So A is another vertex of the triangle, so that means PA is congruent to BP, so PA. And then also C is the other vertex of this triangle, so PC is also congruent to those other two. So those are all the segments that are congruent to BP, PA, and PC because they go from circumcenter to vertex. All right, the next type of segment we're going to look at is an angle bisector. So with angle bisectors, they also have a point of concurrency. So I am just going to real quick try to draw the angle bisectors of this triangle. And we'll find that those angle bisectors all meet in one point. So they are also going to be all concurrent. We'll call the point where they meet P. So the name we give to the point of concurrency for angle bisectors is incenter. So incenter is the point of concurrency for angle bisectors. So incenter pairs with angle bisectors. And it just takes a lot of practice to understand which ones pair up. That angle bisectors pair up with incenters. Circumcenters pair up with perpendicular bisectors, and so on. And so it's called the incenter of the triangle because it inscribes a circle. So point P is going to be the center of this blue circle here. So I've got this blue circle, P is the center. So you notice that from that end center to each side of that circle, that's a radius. Those are all going to be congruent to one another. So just like we had a theorem for circumcenters, we also have a theorem for incenters. And that is that segments from the incenter to a side of the triangle are congruent. So if we were looking at the following triangle, P is the incenter of that triangle, we can see that it is formed by angle bisectors because we have all these marks. So if I wanted to list out the congruent segments in this triangle, they would all have to go from this incenter to the side, not the vertex, of the triangle. So here, PF goes from incenter to a side of the triangle. PD also goes from incenter to side. And then PE also goes from incenter to side. So these three segments would all have to be congruent. So for the incenter, where is it going to be located? Well, for angle bisectors, that point of concurrency will always be inside. So the incenter is always located inside the triangle, no matter what type of triangle it is. So the last example we're going to look at for tonight, and we will be done, is this one. We want to find the measure of the following. The first thing we want to find is PK. So if we're looking at PK, it would be this length here. So that would be PK. And it goes from incenter to the side, so it's congruent to all the other segments that go from incenter to side. So these segments are all congruent. So let's just say that PJ, let's say that it equals we'll say it equals 16. So if PJ equals 16, that means LP also equals 16 and PK also equals 16. I'm going to show you some examples tomorrow where we have to use the fact that we've got right triangles in this picture to help us find lengths. But tonight I don't want you to worry about that. I just want you to recognize that PK has to be the same as PL and PJ. So now we're going to go to number 4. We want to find the measure of angle, and I'm going to delete all my stuff from the last question. We're going to find the measure of angle LZP. That would be this angle right here. Before we do that, I want us to find these angles first. So let's look at the first one. Angle ZYX. Angle ZYX would be this angle here. Since these are angle bisectors, if this bottom angle is 27, this one has to be 27 as well. So that whole angle has to be 27 plus 27, which is 54. Now let's look at the next one. Angle ZXY. So angle ZXY would be this top angle here. So we know that this one is 31. So that means this one must be 31 too, because these are angle bisectors. So this angle would be 2 times 31, which is 62. All right, let's go to the next one. The measure of angle XZY, that would be this angle here. So this one's a little bit trickier. So we know that this angle is 62. We know that this angle is 54. So we've got one big triangle here. They must all add up to 180. So that means that our last angle would just be 180 minus 62 plus 54. So when we do that, we get that that angle is 64 degrees. So this one must be 64. So now I want us to look back at number 4. Number 4 asks you to find the measure of LZP, that green angle. So if this whole black angle is 64, that means that our angle in number 4 must be 64 divided by 2. which is 32. So that's it for tonight. Come in tomorrow. We're going to look at a few more things with these points of concurrency, and then I got some work for you to do. See you then.